Okay, well, oh, there it goes. Okay, well, I'm gonna try to make this go pretty quick. Um, so when I first looked at this, I thought, "Wow, this is crazy. This is a lot," stuff like that. But I think if we take this step by step, it's not as bad as it looks. So the question says, state all the transformations. Doesn't just say translations; it says transformations acting on the functions, state the order in which they would have to be applied to the parent function. I'll be quite honest. I'm not really sure why the order matters, but we're just going to do what it says. So, the way I like to think about this is we want to remove everything. We're just looking at number one for now. We want to remove everything out of this function that is not part of the parent function. So I just Googled types of transformations and then parent function. And this website came up, Math Hints. And this website does a pretty good job. It shows you a lot of the parent functions that we're going to be working with today. And you have some basic stuff in here like y squared or the inverse of it, which is the cube root, or sorry, the square root. Then you have like y to the third, and the cube root over here, and so on and so forth. What is this? Oh, b to the x. So just some parent functions here. We're not going to really worry about the stuff at the bottom, but this is a good place to start. And then down here in this table, it starts to define some transformations for you. So you have up here by adding to the tail end of it. You have down by subtracting. You have something called a stretch, or sometimes called a dilation. We're going to use whatever vocabulary your teachers uses. She might use or he might use dilation, or they might use stretch. The opposite of stretch would be compressed, and all of that is done with a coefficient next to the main term of the parent function. So you can actually see what's being done right here and what it's called here, if that helps. Then we have a reflection, and that's putting a negative 1 coefficient in front of a function. I know there's a lot of information here, but these bolded letters really help. Don't really worry about that one just yet. And so all of this looks like it's being applied. Oh, these are vertical transformations. And so down here we have horizontal transformations. So we have the same type of stuff. We can move it left, we can move it right, we can compress it, and this is all in the horizontal direction. That means this way. Then we have reflection, which is just moving it across or over the y-axis. Then we have the absolute value. And there's a section called mixed transformations here. I guess this will be easy looking at this. So this kind of gives you an order, and it actually says here somewhere, the order doesn't actually matter, but in your instructions on your sheet, it says the order does matter. So we're going to try to keep this order. We're going to look at flipping, and then stretching, then horizontal shifts. So how I would do this is I would remove everything out of this first equation except for y, or f of x. F of x just means a function of x. You're doing something to x. So we're going to consider this, for all intents and purposes, y equals 4 over 3x squared minus 6. We're going to remove the 4 over 3 and we're going to move the negative 6 because it's not part of the parent function. The parent function in this case is this guy right here, y equals x squared. So we're just going to graph that. Here's y equals x squared. So the next thing is we're just going to start adding things. And a good rule of thumb is to add the thing closest to x first. And that usually will get you there. So the first thing we're going to do is we're going to take x squared and we're going to put 4 over 3 in front of it to match it up. Give me 1 sec. I don't think I can pause it. I tutor. Sorry.
Nice. I figured that's what that was.
So when you put this coefficient in front of the x, if we look at our little cheat sheet here, we can go down. We see that this is in the horizontal direction because it's not really moving up and down. So we're going to go down here to horizontal. And here, we're going to see it's compressed. And actually, because the coefficient is outside the parentheses, this is actually going to be a vertical. I lied. Sorry. So we have this situation right here. We're going to call that a vertical stretch. I see what's going on now. So you can imagine this parabola as being pulled upward or stretched in the vertical direction. And it does look like it is compressed horizontally, but it's actually just being stretched vertically. If, just for clarity's sake, if this was written like that, that would be a horizontal stretch or compression, actually. But since we're not squaring the 4/3, we're going to call this a vertical stretch because we have this case right here. So the next thing we're going to do is, at the first step, you would write here 1, vertical stretch by a factor of 4/3 is what I would write that as. I'm sure your teacher has some examples that he worked in class. Try to follow their notation. I don't see any examples here on your piece of paper, so I'm going to do my best to try to cover everything. So the next thing after that is we're going to add, or I guess subtract, this 6. When we do that, we can see we've done something to the graph, and it's kind of hard to see. So let's go ahead and just graph a new function. 4/3 x to the power of 2 minus 6. We can see that this moves the graph down. We've subtracted 6, moving the origin down. So if we want the correct vocabulary for this, we can call this a translation down by 6 units, is what we would call that. So the next thing here would be translation down 6 units. And that's really all that's been done to that first one. You have a dilation or a stretch in the vertical direction of 4/3, and then you have a translation down 6 units here. I'm going to just go through these odd numbers and let you do the even numbers. I might do 6 with you. That's kind of a hard one. So let's go on to 3. All right. So again, let's go through the same function and try to see if we can find the parent function here. I don't know if I saw this one, but I'll check just in case. No, there's no natural logs here. But basically, we're just going to remove everything except for x and this natural log function. So we're going to have y equals natural log of x. That's what we're going to start with right there. Natural log of x. Okay. Then, as a good rule of thumb, like we've said before, the next thing we're going to do is we're going to start throwing things into the function one by one to see what they do to the function. So the first thing we're going to do is we're going to put this negative in there and make that a negative x. As you can see, that reflects it across the y-axis. They might talk about it down here a little bit in this mixed category. Maybe not. Oh, flipping across. Yes, flipping across the axis first. Negative signs is what we were looking for. That's perfect. So we have a flip across the y-axis or a reflection across the y-axis, whatever your teacher uses. for vocabulary on that. That would be the first transformation. The next thing we have, let's stick to this little list right here. We're looking for multiplying and dividing next. So this 5 over 2 is being multiplied. So let's go ahead and throw that in there. And just for clarity's sake, I'm going to do that so you can see the difference. Number 5 over 2. So 2, beautiful. So when we do that, it's kind of hard to see if that's a vertical or a horizontal stretch. So if we go over here to vertical, we can see that if we're taking our function and we're putting the coefficient next to it like that, like right here, I hope you can see my mouse. If we're doing that, then we're going to call that a vertical dilation or a vertical stretch. And you can kind of see that. It looks like somebody's grabbed the top of this black line here and pulled it up to this orange line up here. So we're going to call that a vertical stretch by a factor of 5 over 2. Putting by a factor of 5 over 2 is important because, it could be by a factor of 2, it could be by a factor of 1,000. Describing that transformation is a very important step. So the first thing we did was reflection across the y-axis. Now we have a dilation or a stretch in the vertical direction by a factor of 5 over 2. I think the last thing we have to put into this function is that minus 5. So I'm just going to copy this, put it down there, and subtract 5. Now, it kind of looks like it's been just shifted over 5. And if you ever want to check this, there's a little trick with Desmos. You can put in another variable here, let's say z, and this little button will pop up, and you can have a slider in here. So you can see that as we change this z value, it's moving right and left. And so we're going to subtract 5, so I'm going to move it to 5. And we can see we've moved our previous function here. We've moved our previous function here from its location all the way over to the left 5. So we're going to call this a translation. This translation is in this form right here. And usually we see this as moving our function up and down, but since it's contained within our natural log, you can actually see the effect that this thing has, and it moves it to the left by 5 units. So our first step was we had our parent function, then we reflected it across the y-axis. And then our next step was we had a vertical dilation or a stretch by a factor of 5 over 2. And then we had a horizontal translation to the left 5. That would be the order of transformations. And transformations and translations sound the same, but they're not. Transformations kind of encompass everything. You have like dilations and up and down movement and left and right movement and reflections, all encapsulated in that word transformations, while translations just means sliding. That's all it means. We can go ahead and do number 6. Just a little tip on number 5. You're going to start with y or f of x equals 6 to the power of x. Then you're going to throw in that 3 over 4, see what it does, and then throw in this negative 1.5, see what that does, and then add 10, see what that does. And I think the point of this exercise is just to get you to conceptualize what all of these things are doing to these parent functions. So when you see something on a test or whatever, you can kind of already see the graph in your head. Like just from experience, I know that this negative 1 over 5 is going to flip the graph in one way or another because it's negative, and this plus 10 is going to move the whole thing upwards. So just having experience around this type of thing will really help you. Moving on to number 6, we're going to strip everything out of this equation and just do one thing at a time. So let's do that. Boop, 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 boop. Okay. So our base equation, our parent function, is going to be, we're going to take out as many things as we can without changing the actual shape of the function. So I think our parent function is just going to be y equals x. And Desmos does this by default, but if I was being like completely accurate, I'd put y equals in all these. But Desmos does that by default, so I like it. So I'm just going to put x. So the first thing we're doing, let's go ahead and go back to our little cheat sheet order thing. If I can find it. Here we go. So we're looking for negative signs first. Perfect. There's one right there. So instead of putting the 5 over 3, I'm just going to put the negative sign in. Negative x. And we're going to see what that does. Now, this is kind of hard to see, but this is actually, let me try to better illustrate it here. Well, this can be considered a reflection across the y or the x axis. But I think, actually, because we're here, now we have negative x. Boom. I think it's a shift across, or a reflection across the x axis. That would be vertical. Yeah, this is what we're doing to it right here. If it was a reflection across the y-axis, it'd be inside of whatever's going on. So if it was something like that, but we don't have that. We have a vertical reflection, which means a reflection across the x-axis from these two quadrants up here to these two quadrants down here. Okay. So it might actually help if I kept a little tally. You usually have an untitled document here. There's a lot in this one, so I'm gonna try to keep this in a list form. So we have reflection across x-axis. Okay. Next, we're going to put that 5 over 3 in there. See what happens, because there's no other negative signs. We should be good. So I'm just going to copy this. And this is how I recommend you do this. I can't imagine we're asking you to do this without a calculator just yet. But eventually, hopefully, you'll be able to see this in your head. So because we have something being multiplied to it, we can look here. We have this scenario right here, a similar situation. In this situation, they're multiplying by 4. In our situation, we're multiplying by 3 over 5. So let's see what direction this is in. This is a vertical dilation or a stretch in the vertical direction by a factor of 5 over 3. And 5 over 3 is less than 1, so we expect it to shrink, actually. So we could call this a shrink or a compression in the vertical direction by a factor of 5 over 3. So the next step is we're going to work again from inside out. We're actually going to, we're going to add this 18. So copy this. this. I'm assuming she wants you to do this by order of operations. Yeah. Okay, so this can be confusing because it is a straight line. I could make the case that this red line was shifted over to the right by a factor of 30. Okay? But that really doesn't make sense because we use the number 18, so shifting it to the right 30 doesn't make sense. However, if we go up here and we look at this point right here, we can see that we've also shifted it up by 18 units. So if I was going to ask you which one was more likely, since we added 18 to it, we're going to say that's a vertical translation of 18 units upwards. So I actually forgot to write down the second step. I'm going to call this a vertical dilation by a factor of 5 over 3 or 3 over 5? 3 over 5. 3 over 5. I'm going to say vertical cow. Vertical translation up 18 units. All right, back to our problem here. So we did that. Now we're going to put this 5 in there and see what happens. Boop. 5, boop. All right. This gets interesting. We have a similar situation from step 2 to step 3 where we're looking at a dilation because we're multiplying. But in this case, it looks like it's a little bit more extreme. So if we want to double check ourselves, we have this situation here where we're multiplying what we have right now by a integer or a number. And so we're going to call this a vertical dilation or a stretch. Vertical dilation by a factor of 5. Cool. I think we only have one more. Yep. We got to put this 7 in there. Now it looks like it's 7 plus all this goobity gop, but it really doesn't matter what order we put this in. So 7 plus this, or this plus 7, is the same exact thing. So what I'm going to do is I'm going to cheat a little bit and just go plus 7. Makes it a little easier to see. And if we're looking at this line to this line, it kind of looks like we just moved it over 2.33 units. But again, if we look a little bit closer here, we have this point, and then we have this point right here, right about there, where it's on the same line, and this point has been moved up 7. And since we added 7, we're going to go ahead and say that's what happened. So we're going to say vertical translation up 7 units. Let me check chat, make sure I'm not supposed to be somewhere right now. Whatever. Okay, cool. I've only got a couple minutes left before my recording's going to bug out, but this is what your answer should look like for number 6. Cool. So we've done 1, we've done 3, we've done 6. You should be able to do 2, 4, and 5 on your own. I'll walk you through 7 real quick just to kind of show you what she's looking for. So we're starting with the parent function x squared. Cool. Next thing we're going to be looking for is, let me home that. Boop. Next thing we're looking for is vertically compressed by a factor of 5 over 9. So if we look at our vertical transformations here, and we're looking for a dilation, which is right there because it can be stretched or compressed. we're just going to multiply what we have by that 5/9 factor. So that's easy enough. And boop, like that. So this is a vertical compression of 5/9. I know it doesn't look like it's a compression, but you imagine somebody sitting on this blue line and kind of squishing it down. That's what we're doing here. So next, we need to shift left 7 units. And a lot of people would do that as an instinct. Actually, if we go down here to our horizontal, because we're going left and right, we see that we need to put our factor within the bounds of this function. So I'm just going to take what we have and put in a unit to the left. Now, some reason, whoop, shift left 7 units, not 2. So you would think left might be negative, but left is positive when we're talking about inside these parentheses. So we're going to add 7, and that moves us to the left. You can see it's been moved to the left. Got 4 minutes left. Reflected over the y-axis. So that's a horizontal transformation. And you can see that a horizontal transformation is done by multiplying the inside of our equation by that -1. So what I'm actually going to do is take this whole inside here and multiply it by -1. Oh, not 0. Just the x. So you put that negative in there, and it flips it across the y-axis, which is exactly what they want, reflected over the y-axis. And the last thing we have is a horizontally compressed, I think that's by a factor of 2/3. So we go to our horizontal tab, and we go down here to dilation, and it looks like we need to have that bound inside our function as well. So we're going to put the vertical stuff out here, outside of our function. We're going to put that horizontal stuff right here, and factor of 2/3. So if we do this right, it should look like that. And so this would be our final guy right here. Hope that makes sense. Please let me know if you have any questions. With that, you should be able to do the other half. Good luck and have fun.